So I will talk about diffusion generative models and how we can make use of SMC and different such models. And as you may or may not know, these models have been very popular in machine learning lately as a way of doing synthetic image generation and similar. I should mention before I start that this is based on work most of my PhD student, Fredrik Lindsten. He presented the main part of the talk is based on a paper he presented after the stats a couple of weeks ago. Also, before I get into the actual talk here, if you have any questions throughout the talk, feel free to interrupt. Okay, so generative modeling is really about solving a very fundamental statistical problem, you could say. Just given some training data samples, xi, we want to learn some model, p theta x, which approximates the sort of underlying true data generating distribution, p data. What makes this a bit special when we talk about these kind of modern generative models in machine learning is that we don't parameterize this p theta directly, but instead we do this implicitly by constructing some stochastic procedure that can generate samples from p theta. And typically this involves then simulating some simple noise variable, some standard Gaussians, for instance, and then we propagate this through some neural network, and this will then give us a sample from our model. So these parameters, the theta here in p theta is also then of the neural network. Right, and diffusion generative models is one very popular class of such generative models based on diffusion processes. And I should say, when I say diffusion model throughout this talk, I refer to this kind of class or family of generative models. In particular, a bit later, I will talk about discrete generative models. I can still refer to them as diffusion models because they have something to do with this, but it's not really diffusion. I'm sure that many of you have seen some picture like this before. It tries to illustrate sort of intuitively what such a generative model or how it is trained. So the idea is that we have samples here from our training data set. We denote them by x0. So imagine that a data distribution here is the initial distribution at time 0 of some stochastic process. We then add some artificial noise to this and then simulate the trajectory of the stochastic process until we end up with something which is approximately just standard Gaussian. So this stochastic process is constructed in such a way that it has this standard Gaussian as a stationary or limiting distribution. And then the generative model is sort of trying to reverse the stochastic process. So we start by simulating some standard normal, and then we kind of propagate this backward in time using some other stochastic process. And then at time 0, we then obtain a sample from our p theta. And typically, this kind of diffusion part of the model or the noising part of the model is something simple, say linear Gaussian process, so that we can actually compute sort of conditionally on the x0 here, everything is simple. It's a complicated initial distribution, but conditionally on x0, we can compute all the marginals and so on. And this the backward process is not as simple because, well, it would involve marginalizing with respect to this true data distribution x0 if we want to compute the actual sort of reversal of this. So what we do instead is that we postulate a Markovian backward process, which is, for instance, defined according to taking the actual conditional distribution. If we want to go from, say, time t here, so x at time t to x at time t minus 1, we take the actual conditional distribution of xt minus 1 conditionally on xt and then also conditionally on x0. This thing we can compute. It's just a sort of a Gaussian bridge between 0 and xt. We don't know x0, of course, so what we do instead is that we plug in some estimate here of x0 in this expression for the conditional, and that estimate is obtained using a neural network. So that's kind of one possible view on these models. An alternative view is to take this into continuous time, and then we replace this sort of discrete time linear Gaussian system here with continuous time version. Again, this is typically something simple, like linear Gaussian continuous time. And the reversal of this, well, we can write down what reverse time SDE is, but again, this involves some intractable quantities. Specifically, this thing here is now the score of the kind of the true marginal distribution of the forward process at time t, and this is not known to us. So what we do is that again make use of a neural network to approximate this score here. And we plug in that neural network, numerically solve the backward in time SD, and that defines our generative model. Right, so as you can see, these models have sort of a sequential nature to them, which makes the combination with SMC quite natural. And indeed, we have seen quite a few papers lately that have made use of this connection and applied SMC to this class of generative models. I'm not sure actually why it took so long, because these models have been popular since around 2020 or something, and it's just until recently that we've seen these applications of SMC popping up. I mentioned that to Sheng here at the coffee break, and they said that maybe it just took a few years for the neural networks to finish training. So, right. So this connection with SMC becomes even more apparent if we look at the variation of this problem, which is for conditional generative modeling, which, similar to before, we assume that, well, this conditional generative modeling is really about building a generative model that can simulate from some conditional distribution over X conditionally on some variable Y. This in itself comes in a few different flavors, and I will mention two. And the first one here is simply that we assume that we now observed sort of labeled or annotated training data, so pairs of X's and Y's, and based on those training data points, we want to learn the conditional distribution Px. And in this situation, we can essentially make use of the same algorithms or model formulations as before, but where we simply add this Y variable as a conditioning, as an additional input to the score networks and so on. So conceptually, it's kind of the same problem, but it's also more difficult, because it could, of course, be that for each value of Y here, we observe a single corresponding X value. So we need to, in some way, interpolate between the different conditioning variables to find this conditional distribution. That's one sort of flavor of this problem. The other is that we assume now that we have access to an unconditional model, so data X here, that could be sort of defined by one of these unconditional diffusion models. But then we also have some known likelihood function, so some Py given X, and I simply want to combine this to compute the posterior distribution over X given Y. So we essentially take this diffusion model to define a prior, and then we're interested in solving the corresponding case. Right. The way we will approach these problems is using a technique that has been quite popular as well in this literature, which is referred to as guidance. So guidance essentially just means that starting from such a diffusion-based generative model, we want to modify this SD, the drift in the SD in some way, in order to kind of steer the samples towards the conditioning variable. And this is used quite a lot in this models, both for this first setting here, in order to kind of amplify the effect of the conditioning variable, but also in order to solve this Bayesian inference problem in the second formulation. So guidance also comes in many different forms. I will mention two of those, and the first is what's referred to as classifier guidance. So the idea here of classifier guidance really comes from the situation when we want to condition on a certain class. So y here is some discrete variable, and I mean these models are used a lot in image generation, for instance. Say that you want to generate an image, but you want to condition on what this image should depict. So I want to generate from the cat class or the dog class, to take the classical example in this setting. So so y is some kind of class, and I now want to sample from this conditional distribution. If I'm now going to use a score-based generative model, that means that I need the conditional score. So in classifier guidance, we make use of Bayes' rule essentially to obtain this score. So just take the conditional, we write that as product of likelihood and this kind of unconditional distribution, which of course means that the score that we're interested in can be written as sum of these two terms. This kind of prior score here we obtain using the diffusion model approaches from before, to train this kind of unconditional diffusion model. To get this score of the likelihood term, we train a classifier which approximates this distribution of y given x. So essentially a classifier that takes in the image and then tries to classify what is this image showing. And this classifier then is trained on noisy samples from the data set, so noisy versions of x. And then we replace the score in the generative model with this sort of score. The same idea can also be used for improving the sample or sort of the generative quality or sampling quality of an unconditional model, and this is an approach referred to as discriminator guidance. So the idea in discriminator guidance is, well, now you can forget about the conditional generation problem. Now we're again trying to just sample from some p of x. The idea here is that we take this score that we have learned, we approximate that using, or we have this score network here that approximates the score. But then we kind of acknowledge that this is not perfect. So what we do is that we kind of write this true score of the marginal at time t as our score model, plus a correction term here, which now depends on the true marginal again, which was intractable, and we have the actual generative model. So you can think about this S here as being the score of p theta. So these two terms cancels, and then just left with the score of the marginal u of xt. So we haven't really done anything useful so far, but the idea in discriminator guidance is that we can now try to estimate this ratio here by training some external discriminator, and this is similar to what's done in generative adversarial networks. We train a model to distinguish between sort of generated and real samples. So that's what I mean by this real versus fake discriminator. So we generate noisy samples both by taking actual training data samples and adding noise to them up to some time t, and by generating samples sort of from the final time point and down to time t. And then we train a discriminator to distinguish between those two sets of samples. Based on that discriminator, which I denote by pi here, we can approximate this density ratio. And we take that expression, plug it in here, and we get sort of a correction term in the score. Right, so both of these approaches, both classifier and discriminator guidance, you can see that we have this pre-trained score-based generative model, And then we try to add a correction term of some sorts, which looks like a gradient of log of some function, which I denote by W here. And this leads us naturally into SMC land. So with this formulation, we can interpret this now as being the score of some sort of modified model, which we can then take as a target distribution for SMC, and I refer to this then as the intermediate target at time t, which is given by p theta here, which is essentially a prior that is given by the unconditional diffusion model, and this function w here plays the role as potential. I'm defining this now as an SMC algorithm working backward in time. So we're sampling from capital T down to little t here. It looks a bit awkward, but it sort of has become the convention in this diffusion model literature that the generative model works backward in time, and therefore our SMC sampler here will also work backward in time. But yeah, we get the sequence of intermediate target distributions. We can introduce some proposal distribution for the SMC sampler, and those two together give us an expression for the weight function that is used to compute the importance weights, and we see that this W appears here. And as I said, this has been explored in quite a few papers lately. This is not an exhaustive list of references, but just listed a few that I felt were maybe most relevant to this presentation. So there are two, one that presented in Europe in December last year, and one that will be presented at ICLR. When is ICLR? In a few weeks, I think, this year. So both of these deal with the sort of Bayesian inference problem or problem. And then we have two also recent papers. It's our paper that I mentioned, and then that one that will be presented at CVPR also later this year, deal with the discriminatory guidance version of this. Okay. Questions so far?
Was the weighting functions that includes the same as with the previous discriminator that you have mentioned?
Yeah. So you take essentially whatever you have here in the drift term, that would be your weight. So
not necessarily the one that you learned from the previous discriminator. In the previous slides. Yeah,
so
that one is.
So it will be this thing that will be our W. The discriminator guidance.
After learning the discriminator. Yeah. And is there any way to actually directly estimate the gradients of log of that ratio instead of estimating the ratio?
Probably yes. We have only explored it where we actually train a discriminator in this way. And we also want, not only do you want the score here, but you actually want the same W function in order to evaluate the weight. So I think when looking at these sort of score-based generative models, there's an option if you should either parameterize your neural network to estimate the score directly, or if it should estimate the potential, and then you differentiate through that model to get the score. And to me, it's kind of natural if you want to use both. You want to have the score in your proposal essentially, and you want to have the potential in the weighting to parameterize this potential directly. But I don't know. I think empirical evidence maybe shows that it's quite better to do it like a network, which one network for the score and one network for the potential.
Actually, like also same the previous slide 8. Like this approximation, can you explain it in plain English? What we're looking at? Q divided by P approximate.
Yeah, so here you mean just, or
That's like, yeah, the approximation, the Q, so like the marginal that we have test, like the model. Why is it? I don't understand the equation at all.
where this particular,
What it means.
yeah, so we generate xt from one of these two distributions, you could say, with probability 50-50. And then I give you the xt value. So this you could say is the true distribution that we're interested in. That's what I refer to as the real distribution. And then this is our generative model. That's the fake distribution. The sample from an xt from one of those with the probability. And then I just show you that value of xt and ask which distribution did it come from. And that probability, if you look sort of at an optimal base classifier for that problem, will depend on the density ratio.
Yeah.
That is kind of, if we now assume that this is kind of the optimal base classifier, then this would be an equality.
So it's just the posterior.
So that's quite.
It's just the posterior of the classifier based on the 50-50 prior.
Yeah. Right, so we cannot take what I've said about SMC and so on for these models, put that aside for a little while, and I will talk about discrete generative models and then define this. So discrete generative models is really about generating some kind of discrete objects. And the reason for why we have focused mainly on this is that these sort of score-based, both generative models and score-based guidance techniques are not readily available for applications when X is now a discrete variable. And applications where that might arise that we have been, I think there are plenty of application areas, but we are interested in generating things like molecular graphs or what's shown here. This is sort of a representation of a crystal, so generating materials. This illustrates what's referred to as a Wyckoff representation of that, which is sort of a discrete representation of a crystal structure. And as I said, in such situations, we don't really have the score, so we can't make use of regular. Here, SMC comes in handy. So for this, we will now assume that we have our variable of interest that want to generate X. It's still sort of a vector with the components here, but where each component is a discrete variable. For simplicity, I will just assume that they all have sort of S possible values. So there are, of course, many different ways in which we can construct generative models for such data. But in order to stick somewhat close to what we have seen so far, we can still make use of the same idea of generating now a diffusion process where we first take a sample from the training data, we simulate some stochastic process in order to kind of noise, add more and more noise to this so that we eventually end up with something that is simple to sample from, and then we try to learn the reversal of that stochastic process. One possibility is to make use of a discrete Markov chain, which operates sort of on each coordinate of this vector X independently, which means that we have some transition probability Q here, which tells us how to transition from state, well, some state at time t-1 to the next state or next time step next. And based on this destructive process, our generative process, which tries to reverse this, can be constructed, for instance, in this way, where we sample each coordinate of this vector independently. Similarly to before, we have some neural network here which tries to reconstruct the noise-free sample from a noisy one. So we observe xt, we try to predict the probability over x0. And given that, we can work out what the probability of xt-1 is. So here we actually marginalize over the x0, so we don't just plug in the point prediction here, but we do this one coordinate at a time. So there's of course an approximation here still. And this method is one which was proposed in this paper here. It's referred to as 3PM, so discrete denoising diffusion probability. Okay, so in this paper, they also discuss different ways of constructing this noising process. And one observation that we can make is that unless there's some kind of ordinal structure, discrete variable, transitioning sort of into some other discrete state, as soon as we are kind of left where we are, there's little information about where we came from. So it's quite different from the situation with a Gaussian diffusion, where we add a little bit of noise each time step. So based on that observation, they also proposed a version of this where we don't sort of jump back and forth between these discrete states, but instead have an absorbing state in the Markov chain, which is such that if any coordinate enters that absorbing state, it remains there. So we simply extend the state space here with this null symbol and the probability of transitioning from the null symbol to this one. So you can then imagine or think about this as when we apply this kind of noising process, you take a sample and then you randomly mask out the different coordinates of the x vector until we're left with just the completely masked sample. And furthermore, if we do this with a low enough transition rate so that at any sort of time step we only mask out one coordinate, well, if we do it with a low enough transition rate, then at each time step we'll only mask out one single coordinate. And looking at this, I realized that it's actually quite similar to an autoregressive model. So an autoregressive model that samples the coordinates of this x vector one at a time. And specifically, since the order in which we mask out these elements is random, it's similar to what's referred to as an order agnostic autoregressive model. So these models are essentially just based on this factorization of the joint PDF over this vector x, which is sort of an autoregressive factorization, but where the order of this product is given by random permutation sigma. And in these order agnostic autoregressive models, we then try to learn these conditional distributions for any essentially any conditioning, so that we could have an arbitrary permutation here and still simulate this using an ancestral sample in one coordinate. Okay. As I said, we have used this for simulating stuff like molecular graphs and similar. So I have one slide or a couple of slides here just showing a small modification, which is also used then when I'll show some numerical results later. So briefly mention this, that even though we could apply these denoising diffusion models or the model directly to these graphs, or we similarly than these order agnostic autoregressive models, it might also be easier to learn the joint distribution if we also limit the support of the possible permutations that we can consider in some way. To hopefully give you some sort of intuition for that is that if we want to generate a graph, say that we now have both node variables and edge variables here. So these node variables are, but it's a labeled graph. So each node variable can take a discrete label. And then we have edge variables, which, well, since we want to generate the graph, we don't know if there should be an edge between any pair of variables. So these are essentially binary variables, which tells us whether there should be an edge between nodes U and B. Then if we approach this and don't sort of make any distinction between the x's and the e's here and just apply a random permutation, then we could of course have a situation where I need to generate an edge between two nodes that are still sort of in their masked state. So I'm not really sure what will be in these two nodes. And intuitively, that would be more difficult than if I actually know what these nodes are. In the context of generating a molecule, that would mean if I know what type of atoms that we have here, would I generate the bond or not? So the small modification that we have used working with this is that we essentially generate the nodes and edges in a more ordered fashion. So we essentially generate the nodes first and then generate the edges between the newly generated node and all previously generated nodes. And just an illustration what that might look like. So if I want to generate a molecular graph here, the first thing that I do is that I place a node here. It's still in its sort of masked state, so I'm not sure what type of atom this is, but the first thing that I do is always to generate the next thing is that I place another atom in the graph before generating the possible edge between these two. I generate a value for that, and then I generate the value for the edge. And here, also the edges can be like either if there should be no edge, a single bond, or and then we proceed in the same way. That's another atom, generate the value for that, and then the edges. And as I said, a possible value for an edge could also be no edge. And then, yeah, we continue in the same manner. Right, so equipped with this, we can now bring back what we said about SMC and guidance and see how we can make use of discriminator guidance for this type of graph generation. So essentially what it boils down to is that we, at any state of the generative process, we have some incomplete graph like this. Let's say that I want to generate a value for this node. My neural network will predict some probability distribution over possible node labels or atom types. For each of those possible values, I can plug this partially generated molecule into my discriminator, which tells me if it looks legit or not. This gives me some probabilities for real versus fake, and I multiply those with the probabilities given by this neural network here and update the class probabilities accordingly. And then I simulate from that distribution. So this is the first algorithm that we considered, which we refer to as autoregressive discriminator guidance. So this is just, there's no SMC in this algorithm. It just sort of modifies these probabilities that come out from the sort of the pure generative model with the weights coming from the discriminator. We multiply these two together, normalize it, and then simulate from that instead. But we can, of course, also consider SMC versions of this. So what we do is, well, similar to before, define a sequence of target distributions, our model, weight function or potential function. And we introduce some proposal and we get this. And also here we have considered two different versions. So one is based on something similar to bootstrap filter, where we simulate according to the generative model itself, and we use the discriminator just to compute importance weights. So this is nice because we don't have to evaluate our discriminator for all possible candidates of the xk value that we want to sample. There's only sort of one discriminator evaluation per type step. But the downside is that the discriminator that we have learned only affects or influences the weight function and not the actual proposal. So then we also consider a fully adapted SMC version. which is more efficient, but also more costly per time step. So the idea is now that we define our proposal, also similarly to the RTG, the product between the generative model and this potential. We also have these auxiliary resampling weights that are the optimal ones or locally optimal ones in the %, and we obtain importance weights that are identical to or equal to 1. So as I said, get locally optimal proposals. We have a better utilization of the discriminator that we're trained, but it's also more expensive since we need to evaluate and normalize this expression for all possible values of the next state. Okay, so some final notes here is that these SMC versions, even if I would run them with a single particle, are expected to be hopefully quite okay, because they just reduce to simpler versions of the generative model. And in particular, if I take the bootstrap version with 1 particle, that will be equal to just simulating from the original diffusion model or autoregressive model. And the hope is that that in itself is okay, and we can use this then to boost the performance further. Similarly, with the fully adapted implementation of the SMC algorithm with 1 particle, this reduces to this first algorithm that I mentioned, the RTG. And this also means that when we apply this, we typically do it not as you might run a particle filter for solving a filtering problem, but rather we run multiple SMC algorithms with quite a few particles. And the reason for this is that when we work with generative modeling, we're typically interested in getting a large diversity of samples out of the generative model. Whereas if we just apply 1 SMC algorithm with a lot of particles here, there will be interaction between those particles and they will sort of degenerate. So this can then result in reduced sample diversity. So then, as I said, instead we run multiple independent SMC samplers with few particles, and the number of particles can be viewed as some kind of tuning knob for moving from one of these kind of base algorithms to something more efficient. And yeah, table with numbers, never fun to watch, but just to show some results. So we apply this to generating molecules based on the Moses dataset, which is one of the datasets domain. So it consists of some 2 million small drug-like molecules. Based on that, we try to build a generative model that can simulate sort of new plausible molecules, essentially. And we evaluate this, so it's a benchmark data set, as I said, so they had a bunch of evaluation metrics that they proposed in the paper where this was introduced. Now I forgot to add the reference there. For instance, looking at validity of the resulting molecules, this is essentially based on trying to convert or compute the corresponding SMILE strength of the molecule. If that fails or not, well, if it succeeds, then it's valid. Novelty has to do with how many of the valid molecules that were part of the training data sets. So if it's novel, then it's not part of the training data set. And yeah, we have a few more. I can go into the details if anyone is really interested. I'm not a chemist, so I don't know much about it, but different sort of metrics for evaluating how good the molecule is in some sense, how close to the training data. And the results are really as expected, sort of that we get a gradual improvement in essentially all the metrics here as we move from the basic generative model, adding the discriminated guidance with the bootstrap filter a little bit better, and with a fully adapted, it's and the only score where we do actually worse with the SMC samplers is in novelty. But it could also be noted then that the novelty here is computed only for the valid molecules. So what we're really interested in is to get both valid and novel molecules. And if we multiply those together, we can see that the total number of interesting molecules, total proportion of interesting molecules is still large. So in summary, diffusion models are used for a lot of interesting problems in machine learning today, and SMC is sort of a natural fit for combine with these models. And I focus now on this idea of guidance, which can be used both for conditional generation and for improving the quality of the score-free guidance, or SMC enables score-free guidance, which can be particularly interesting than the discrete set.
Time for a few questions. Yeah, I understood this correctly. But when you typically adapted that requires summing over all possible or the entire state space, right?
Yeah, for one coordinate, since we do this a progressive formulation. So it's one take the molecule generation sample, and we generate one atom at a time, and then we sum over all possible values of that. And we're not looking at the entire sort of periodic table here, but it's more constrained. So we're working with 8 different. So something like that.
Yes, for the example where you generated the molecules, you had a huge data set, right, to train the model. Do you have an idea what order is required to get some results for the generative model? So how many training samples do you need in general?
To get some results in the sense of getting something reasonable out of it, or
Yes, something novel.
I think that the challenge is to get something novel and valid. So I think if you have a too small data set, you will probably still get novel samples, but they might not be looking like real molecules, because the model is only learning what sort of what the molecule should look like based on the training data samples. We also work, now I showed you one examples, and including one which is a smaller molecule data set as well, and there I think it's only like 60,000 training data.
Thank you. Any other questions? Thank Fredrik again then.
Okay, we have now just a break, and then at 4:30 we should start with the posters. Those presenters know that they need to put the posters, and hopefully magically it's already prepared there. Okay.
We can see you outside.
We'll see you your last day. It's fine. Just let the people on the first day just
So I talk about it, and then people have questions.
I think distribute at your post, so to be a lot of redundancy. You have if you have many questions, then maybe you know. Yeah, hopefully I can have did she said that it's okay?
Yeah, she already said.
Nada, no pasa nada. No sé, no creo ni que esté numerado. Bueno, no sé. Vosotros, porque no. Me ha dicho que iban a estar así poniendo, lo vamos a mirar ahora. Pero nada.